All right, we're going to continue with looking at the Fourier transform, and we're going to specifically dive down on a really important property called convolution and how to evaluate convolutions. It turns out, especially for LTI systems, that this convolutional property will be really beneficial for us in terms of constructing solutions and outputs to LTI systems. So remember what the Fourier transform looks like. I always like to put this back up here. It is a mapping from the time domain to the frequency domain and back. Okay, it's a linear transformation. The last lecture we covered, we actually talked about all the nice properties that we have once we commit to using this Fourier representation. And so the idea is we want to evaluate all the advantages that we have in moving to the Fourier domain and representing our signals in the Fourier domain. In the last lecture, we talked about things like, for instance, differentiation is very nicely done in the Fourier domain. And so we can take advantage of that in doing operations to our signals. And in here, I want to highlight one of the operations we're going to use all the time, and it's going to be related to convolution. And so, in fact, convolution or multiplication of signals, this is going to be something really important for us in terms of basic signal processing design and applications. So first of all, let's talk about the solutions to LTI systems. If you go back to many lectures ago now, earlier in the lectures when we talked about linear time invariant systems, this was the solution to the linear time invariant system. What we had is y of t is the output of that system. We had a signal x of t, so there it is. And we're integrating that signal against the response h of t. So in other words, I put in a signal to the LTI system. I have this fundamental unit response h, and our solution was just this convolutional integral right here. Okay? So the question is, how does this relate to the Fourier transform? So let's go ahead and start to actually evaluate this representation of solutions in terms of a Fourier transform. So if you remember, a Fourier transform is just given here now of a signal y of t. It's just given by this representation here. It's just integrate its Fourier components against e I omega t, and you come back into the time domain y of t. Okay, so this is just the definition of y of t in terms of its Fourier components. And so what we can do is say, well, what is y of I omega? Well, what I'm going to do is now say, well, wait a minute. So I'm going to represent my signal y of t here as the following. So this is the inverse Fourier transform, and I'm going to inverse y of t. By the way, this y of t comes from this right here, my LTI system solution. So that's what I have here, times e to the minus omega t. So this is just the inverse Fourier transform of the signal y of t, where I've assumed the signal y of t is made up of x of tau and h of t minus tau. Okay? That's my LTI solution. I put it in here, and now what we're going to do is we are going to change the order of integration in this. So let's go back to here. So here's the representation, and now let's exchange the order of integration operations, and this is what you would get here. So I'm going to first integrate with respect to t, then integrate with respect to tau. Okay? So that's what you're going to get here. Now the x of tau is out, and now I have an integral here of h of t minus tau d tau e to the minus omega t. So what this is, it's actually the Fourier transform of h, except for now with a time shift, right, with respect to tau. And in fact, then you can say, well, we already know what happens with time shifts. Time shifts are just leading to a phase shift. And so this is the phase shift I pick up from that. And h of I omega is the Fourier transform of h itself. So this is just using our standard time translation property that we had in the last lecture to get out this here as the representation of the signal y omega. Okay, now the last thing to talk about here is that once we have this is the Fourier transform of the output. Notice that we have the signal x, and we have the Fourier transform of h there. And by the way, We can then pull out this h of I omega because it's now just some constant with respect to omega, and we're integrating with respect to tau. So I pull that out of the integral, and I have this here. And if you look at this, this is the Fourier transform of x itself. So there you go. This is what we get at the end. So if I want to know what the Fourier transform is of that signal y it's just the Fourier transform of h times the Fourier transform of x. So the alternative way to solve the LTI system is you just take your input signal and you take its fundamental response h, you take the Fourier transform of each one and just multiply it together. That does the convolution for you. So in other words, one way to think about convolution is that essentially if you take the signal y of t and you say, well, this is typically my LTI solution, which is a convolution between h and x, it's equivalent in the Fourier domain of just saying, all right, in the Fourier domain, this is just simply a product of the Fourier transform of h times the Fourier transform of x. So think about how I'd solve this solution then. If I had a fundamental response, h, and the signal x, I'd Fourier transform both, multiply them together, inverse Fourier transform. You're done. I don't have to do any of these complicated convolution integrals. I just multiply two Fourier transform pairs together and I'm done. So this is really a powerful concept, right? Because now it's a simple manipulation. In the Fourier domain, it's really trivial to think about how the response and the signal interact. It's just a product of their Fourier transforms. So it's really nice representation, used all the time because it's very easy to compute the Fourier transforms, and then obviously multiplication is a pretty simple task as well. This is the important point. Convolution is the product of the Fourier transforms, and we're going to use that all the time. It's a much more efficient way to do signal processing. Again, if you think about this entire philosophy, what we're going to try to do is say, if I move into the Fourier domain, what are the benefits? Well, right here is one of the big benefits that you have available to you, right? This is like one of the, for LTI systems, this is a huge benefit because all you have to do is just Fourier transform your fundamental response. And then even as you get new signals coming in, if you've just Fourier transformed the fundamental response once, you have it. And so you just have the new signal, Fourier transform it, multiply it against the Fourier transform of the response, and then inverse Fourier transform. FFT, IFFT. It's as simple as that. This is the beauty of this kind of architecture. So another way to think about some of these things too in terms of equivalent systems is if you come in and you do these transforms, the order of these transform operations doesn't matter, right? So you can come in, you can transform this through Fourier transform to H2 to get an output. This is equivalent if you just product them or if you reverse that operation. So all these are sort of equivalent systems when I start thinking about it in the Fourier domain. So again, the Fourier domain representation has so many advantageous properties, and this is why, even when we think about this book, we're spending all this time with Fourier series and Fourier transform, is because essentially you get all of these amazing properties to happen in the Fourier domain. This is why the Fourier transform is the most important of transforms you'll probably ever learn, and because of all the advantageous properties. And I just showed you another one, right, which is simple way to solve LTI systems. All right, so let's go ahead and do an example. Here's an example. I come in with a signal, x of t, which is just here. It's some exponentially decaying times some u of t, so it's on switch, right? So it comes on at time 0. And let's say my response is e to the minus a of t, use of t. So if you wanted to solve this with the LTI solution, right, you would have to do a convolution between these two. Or you can just simply say, well, I know what the Fourier transform, in fact, 2 lectures ago, we worked out the Fourier transform of what this looks like generically. So here's the Fourier transform of x, here's the transform of h. And if you want to know what an LTI system does, you just take the product of those two, and there you go. That is the Fourier transform of y, which is the product of those two Fourier transforms. So I I now have the representation of the output of my LTI system in terms of the Fourier domain, which is here. So now all I have to do is, if I want y of t, I just have to inverse Fourier transform this. And you can actually look this up in the table, or you can work this out pretty easily, which is to say, if you do partial fractions, you can take this here and you break it down into two components. Here they are. There's a scaling factor out front. This is as long as b is not equal to a. You can work out the case when b is equal to a pretty easily too, but b is not equal to a, you get this term, and this term. These have very simple Fourier transforms back if you look at a Fourier transform table, and so what you end up with is this is your solution here as the output. So you just invert that, and there you go. You get e to the minus at ut minus e to the minus bt ut. This is the output of that LTI system. And notice all I did was I took my signal, I Fourier transformed it. I took my fundamental response, I Fourier transformed it. Multiplied the two transforms together, and then just invert that. So of course here we're working it out by hand, right? So if you look at what we got here in these formulas, this is working it out by hand. But in practice, what you would do, you say, oh, this is trivial to do. FFT the x, FFT the h, multiply them, IFFT. Okay, three very simple pieces of code of what you would be doing to do this in practice in a real signal processing application. Okay, so that's the convolution with FFT. It just simply uses the FFT and multiplying the Fourier domain, and you get all this really nice properties, and you get the solution to the LTI system, which is great. Okay, so now we're going to think about the idea of multiplication, which is what if I have two time signals? Notice what I was doing previously. I was multiplying two frequency signals, right? So I have the Fourier transform of one signal, Fourier transform of the other. We were multiplying in the Fourier domain. What happens when I create a new signal, which is a product of two signals? In other words, what people often think about here is I have a signal x, and I modulate that signal x with y. So, amplitude. So I can modulate the amplitude of a signal with another signal. This is what this represents. And so this is something that happens all the time, signal modulation, and this is a generic representation of that process of taking a signal and modulating that signal. And so what we'd like to understand is if I have z of t and I Fourier transform it, what is the effect of this product? Well, because of the duality of the Fourier transform, that product also, remember that this is directly related to convolutions, so one signal modulating another is going to create this system where essentially the Fourier transform of z is going to be the Fourier coefficients of x with y shifted. This is a convolution integral. This is exactly what we saw previously when we took two signals in the Fourier domain. In the time domain, it was two signals that were convolved with each other. For instance, in the LTI system, x convolved with h becomes just multiplication. Now, convolution in the Fourier domain is equal to multiplication in the time domain. Okay, so this is just a duality argument between the two. And then the question is, what does this mean for us? And it actually has some really interesting implications here, because what we're going to think about doing here again is we're using one signal to modify the other for some signal processing operations. And so now you can start thinking about what kind of modulation of the original signal do I want to do to manipulate it to do something, advantageous or favorable or part of my signal processing design. So let's take two signals, x and y, and let's ask ourselves some questions about this. So I'm going to do an example here where the signal y, okay, is going to be a cosine omega naught t. And we're going to use the signal y to modulate x. And we're going to see what happens to x when I multiply these signals together. So first of all, what it tells me is that if I know what x looks like in the Fourier domain and y looks like in the Fourier domain, I'll be able to do these manipulations nicely. So if I take this signal y of t, I already know that in the Fourier domain, right, the Fourier transform of cosine is two delta functions, two spikes of delta functions, one with size pi at plus omega naught, one spike pi at minus omega naught. Okay, so that's the Fourier transform of this thing. And then What's going to happen now, though, is when I convolve these in the Fourier domain, remember that this thing here now gets shifted. So what I'm really saying is I've got this cosine transform, which has these two spikes, but now I'm going to convolve those against some signal xi omega, and then we're going to start asking what happens. Well, when you convolve those, there are going to be these two spikes, it's two delta function spikes, right, are going to sift out the Fourier transform of the signal x shifted by omega naught and shifted by minus omega naught. That was the impact of having this signal here modulating this whatever x is, right? Is it actually creates, notice what it does, it gives me now, z is, oh, it's got one portion of the signal, another portion of the signal, now I can inverse Fourier transform that. So let me give you an example of it, and here it is. So maybe my original signal x looks something like this in the Fourier domain. Here's what the cosine looked like. And when I convolve these two together, here is what the Fourier, here's what the new signal looks like in the Fourier domain. And so now I would inverse Fourier transform this to get my new signal z of t, where all I did was I modulated my underlying signal x of t by a cosine, and now here's its Fourier representation once I modulate it. That was the impact that cosine had on this. So that's the idea. Use one signal to modulate another to perform some kind of task. So I'm going to give you another example of this. Here's an example, and this is, drawn in block diagram form, where what we're going to do is come in with the signal x of t, and what we're going to do is we're going to convolve it with just e to the I omega naught omega ct. Okay, we're going to just multiply this signal coming in by this signal here. And then the question is, what are the implications of this, right? What does that do? So I'm using this here as a modulation of this signal to come into my system. And then what's going to happen is I'm going to low pass filter it, come back out, and then undo that signal modulation and see what do I get out. Okay? So that's going to be the objective. So what can I possibly gain by taking a signal and modulating it with another signal? And you'll see this is quite impressive what can happen here when you use this idea of one signal modulating another. So let me give you an example. I'm going to walk this through in pictures because I think it's pretty powerful. So you come in with a signal, x, whose Fourier transform looks something like this. So this is what it represents. Now, what you do is you modulate it now by multiplying it by that simple modulation here. Let me give it here, which is this here. I'm going to now multiply by this signal. Okay? And what ends up happening is that signal, remember that e to the I omega c shifts it in time. It corresponds to shifting this thing. So now you took this whole thing, you shifted it over here. Okay? That was just what happened when you modulated the signal. It took this thing from here, shifted it over. And it shifted over by some omega c. Okay? So you brought this thing in, you modulated the signal, now its Fourier domain gets shifted over. But now remember, I'm going to go through a bandpass filter. That's what that system had. So the bandpass filter still works at a low-pass filter. There it is. It's going to pull out this part of the signal. And now when you undo the shift, it's going to bring this back out over to here. Okay? So you're going to shift it in frequency, do a filtering operation, undo the modulation, it's going to shift it back into position. So what you effectively did is you used a low-pass filter, which is pulling frequencies from here. But by modulating this, you shifted it over, and what you effectively did is you did a bandpass operation. So the action of having that extra signal modulating your signal was to create a bandpass filter from a low-pass filter. Okay, so these are the kind of operations you can do that are fairly sophisticated, right? In the sense that you can take any underlying signal, and if you have the ability to modulate it, you modulate it for some purpose. In this case here, we modulate it to create a bandpass filtering operation. And that was just done by just simple modulating by e to the I omega c. That's it. And so you can get quite sophisticated with these kind of operations in these modulations to generate desired output. So another way to think about this, and I've shown you two really important pieces of information in this lecture. One is this idea of convolution, which is if you're in an LTI system, all you have to do is take the Fourier transform of the response H and the input signal X, multiply them together in inverse Fourier transform, and you have your output. Okay, that is a super powerful idea. The second thing I showed you is because of this duality property, and this, again related to convolution, in the time domain, if I multiply signals, in other words, I use one signal to modulate a second signal, then I actually can perform very sophisticated operations because what it does now is it convolves those in the Fourier domain. And what I can do is do very simple operations of amplitude modulation to make interesting filters, make a low-pass filter and a high-pass filter, or many other things that I might want to do with a signal just by simply modulating it and taking advantage of the convolution properties now that are going to happen in the Fourier domain. So those are the kind of things we should be thinking about or need to be thinking about. And again, the Fourier domain is just it is the natural place to represent all of this. It's this beautiful coordinate system. And again, I want you to think about it as a coordinate system where we can do all these very advanced things very simply. And we have a very fast pathway in and out through the fast Fourier transform, which is going to be our workhorse tool for doing all of this.